Welcome to a course on classical physics. This is the second video in a comprehensive series where we are exploring all the fundamental concepts of classical physics. We will start with the essential building blocks before gradually moving into more complex topics like motion, force, energy, momentum, and so on. Along the way, we will break down concepts, provide practical examples, and demonstrate how classical physics helps to explain the natural phenomena around us. By the end of this series, you will have a solid grasp of the fundamental ideas that have shaped modern science and engineering. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the second video on a course on classical physics. Well, in the first video, if you have not looked, I will request you to have a look onto that. We dealt with basically the fundamental units, what is time, kilogram, mass, etc. In this video, as the thumbnail suggests, we will look motion along a straight line. But first, we would like to explore what is physics when we talk about motion. Now, one of the purpose of physics is to study the motion of objects. This is how fast they move, for example, and how far also they move in a certain given amount of time. So how fast they move and how far they move. Now, for example, geologists use this physics to measure tectonic plate motion as they attempt to predict earthquakes. Medical researchers need this physics to map the blood flow through a patient when diagnosing a partially closed artery, and motorists use to determine how they might slow sufficiently when their radar detector sounds a warning. There are countless other examples, and however, in this particular video and this lesson, we will study the physics of motion where the object moves along a single axis. So we come to the next part of our video, which is called the motion. Now, the world around us, as we see, everything around it moves, although it seems stationary things such as a roadway, but it moves with the Earth's rotation. Now, in this context, it would be worthwhile to mention one particular historical event which would cite motion. That is, in 1632, Galileo published Dialogue Concerning the Two Chief World Systems, a book that presented arguments for heliocentrism. Now, this book actually brought him into conflict with the church, which had already condemned the heliocentric model as heretical. Now, the phrase "eppur si muove" or "and yet it moves" is said to have been uttered by Galileo after his recantation as a whispered expression of his unwavering belief that the earth does indeed move around the sun. The legend suggests that even though he had been forced to deny the truth, Galileo could not suppress his conviction in the scientific fact "eppur si muove", and yet it moves. So as you see that the Earth's orbit around the Sun's orbit around the center of the Milky Way galaxy, and that galaxy's migration related to other galaxies. So the classification of this comparison is called kinematics, and the question is that what exactly do you measure and how do you compare? And that is what is the primary objective of the measurement of physics. Now, before we move ahead, there are certain important things that we need to mention regarding the motion. The first thing is that the motion is along a straight line only. The line may be vertical, horizontal, or slanted, but it must be straight. Second is that forces, push and pulls, cause motion, but we will discuss it in the later part of the series. In this chapter or in this video, we will discuss only the motion itself and changes in the motion. Does the moving object speed up, slow down, stop, or reverse direction? If the motion does change, how is the time involved in these changes? And the motion of the moving object is either a particle or an object that moves like a particle, such that every portion moves in the same direction and at the same rate. So this brings us to two important conclusions. The first one is that kinematics is the study of motion, including classification and comparison, and acceleration, deceleration, stopping and reversing direction actually are some of the key aspects which we are obviously going to study. This brings us to the next part of our video, which is called position and displacement. What is that in terms of classical physics and measurement coming up into the next part of our video. So when we try to locate something, I have used a magnifying glass just to make things understand that in order to locate an object means basically to find its position relative to some reference point, which is basically called the origin. Now here, as you can see, that there is a positive direction and there is a negative direction of the axis. And it means the increasing number of the coordinates, which is on the right, and the opposite is the negative direction. So for example, if we draw this in order to understand, say for example 0 up to 10, if a particle might be located at x equals to 5 meter, which means it is at 5 meter in the positive direction from the origin. If it was located at x equals to minus 5m, it would be just as far from the origin but in the opposite direction. On the axis, a coordinate of a minus 5 meter can be called as less than 1 meter, and both coordinates are less than a coordinate of plus 5 meter. Now, most important is that we should note that a plus sign for a coordinate is needed to be shown, but a minus sign must always be shown. So plus sign, I mean to say, is not always necessary. We can omit that, but a minus sign should always be shown. Now, when we talk of the change of a position, for example, if we take two positions, x1 and x2, and if there is a change with the same kind of a map or the pictorial representation, if it goes from x1 to x2, we call it as displacement, which is denoted by the Greek letter delta x, and which is called as delta x equals to x2 minus x1. So the symbol delta, the Greek uppercase delta I should say, represents a change in quantity, and it means the final value of that quantity minus the initial value. When numbers are inserted for the positive x1 and x2 value, for example, it moves in this direction, a displacement is said to be in the positive direction, and if it moves in the opposite part, it is called, it comes in the negative direction. So if the particle moves, say for example x1 equal to 5m to x2 is equal to 2m, then the displacement obviously is plus 7 meter. The positive result indicates that the motion is in the positive direction if the particle moves in this direction, and if the particle moves from x1 equals to 5 to 1 meter, then it would be minus 4 meter, and this involves a negative direction which would be shown in this part. So one thing which comes out from our discussion, which is very, very important, is that displacement, actually the number of meters are covered in a trip, is actually irrelevant, and displacement involves only the original and the final positions. Now let us take another example. As we have noted that the actual number of meters covered for a trip, now let me go back, yes, the actual numbers of meters covered in a trip is irrelevant. Displacement involves the original and the final position. Now for example, this is a particle, or this is the two position, x equal to 5m and x equal to 200m, and if the particle, for example, it goes from this position, the particle moves to this position and then bounces back and comes back to this position. Again, let me show you. The particle moves from this position to this position and then again comes back to this position. So the displacement from start to finish for this kind of a position, it would take this kind of a curved path. It would be 5x minus 5m, 5m minus 5m, which will be 0. So this, if it goes back and again it comes back, it bounces back, the displacement is equal to 0. Now also what is important is that a plus sign for a displacement need to be shown, but a minus sign, as I have told earlier, can be ignored. Now if we ignore what we call the sign, that is the direction of a displacement, we are left with what is called just the magnitude. So this is important. If we ignore the sign and thus the direction of a displacement, we are left with magnitude of the displacement. For example, delta x equals to minus 4m has a magnitude of this much. It is also important to note that displacement is definitely a vector quantity, which is a quantity that has both direction and magnitude, and we will explore more on that. But there are two important features. First one is its magnitude is the distance, such as the number of meters between the original and final position, and second is that its direction from original position to final position can be represented by a plus or a minus sign if the motion is along a single axis. From here we move to the next part of our video, that is displacement is a vector quantity, we move to the next part of the video, which is calculating what is called the average velocity and average speed, coming up into the next part of our video. Now, a very compact and easy way to describe a position with the graph of with a graph of position x plotted along with a function time graph t. So the notation, for example, if I take this kind of a graph, and here you can see the notation xt, this one, I'm so sorry, yeah, the notation xt represents a function x of t and not a product x times t. Now what I'm going to do is that I'm going to take a cute little animal which is called armadillo, and for example the armadillo is right over here, so it shows that it is at the same position for any time. That means that the position function for a stationary armadillo over a 7 times a second's time interval, the position stays at x equals to minus 2m. And this one xt represents a function of x of t, which I told. So from this graph, what becomes important is that the graph x for t for an armadillo that is stationary of x equals to minus t meter, the value of x equals to minus tm is true for all the times of t, that is time. So it is same at all the position, that is why it shows a green line, straight line, green straight line. Now more interesting is that when it involves motion. Now let us put this kind of a graph, and what I'm going to do particularly is that I'm going to take the same armadillo. Now the armadillo first is noticed over here, and it gives us first at a notice t equals to 0 when the position is x equals to 5 meter, and it moves in this direction. Let us see. So the armadillo is moving from here to, it goes up to here. So initially it was here, now it goes up to here. Now as soon as it moves towards x equal to 0, it passes through the point, this one which is 3 seconds, it is at position x equal to 0, passes through the point, that point at t equal to 3 seconds. And then it moves further into this position. So the armadillo now from here, now slowly moves up to this position. So when it moves up to this position, what we get is at position x equals to 2, when time equals to 4 seconds. Approximately, you can just join those lines. So it is something that, like I would see, the figure is more abstract and it reveals how the armadillo moves. So first let me again show you. First it was here, it moved up to here, and at this position x equals to 0 and time equals to 3. Then again it moves from here to here, and this is at position x equal to 2 when time is equals to 4. So what shows is basically the straight line position, and it moves in a straight line of the armadillo. So first it moves t equal to 0, and then a position x equal to minus 5, then again x equal to 0 at t equals to 3, and so on. So this gives you a kind of a pictorial and a graphical understanding of how position and displacement happens. Now there are several quantities which are associated with this phrase, how fast, and one of them is basically called average velocity, which we denote by v average, which is a ratio of the displacement of delta x that occurs during a particular time period delta t, and to that interval we say the equation looks like this. So the notation means that the position is x1 at a time t1 and then at x2 at a time t2. A common unit for average velocity is the meter per second, but there can be other units in the problems, but they are more or less in the form of length per time. Now on a graph, if we notice this kind of a graph where the x versus t, right, so this is the x versus t, then I would say the slope of the straight line that connects the two particular points. So this is the graph which is going up. Let us see again. So this is the curve which is going on. These are the 2 points, and the straight line which connects the slope. So let us see. Here it connects. Again, here it connects. So the straight line that connects 2 particular points on the xt curve, one is the point that corresponds to x2 and t2, and the other point corresponds to x1 and t1. So likewise, what we mean to say that when the displacement has both magnitude and direction. Its magnitude is the line slope. When it is going up, we call the average velocity positive. It is going something like this, then we call it is negative. So the average velocity has got both magnitude and direction. So positive average velocity tells us the line slants upwards, and the negative average velocity tells us that this line goes downwards. And the average velocity always has the sign as the displacement delta x, because of delta t is always positive, and it has got a magnitude and direction. Now what we get from here is that if we go to the next part, so here what we can do is that we get to find the average velocity. So it will be change in position by change in time, so we can get something like this. But remember, there is one important thing, is that the average speed is a different way of describing how particles move. So the first one which we saw over here, this is basically for a given time interval the average velocity. But average speed is a different way of describing how fast a particle moves, because whereas average velocity involves the particle displacement, the average speed actually involves the total distance covered. So average speed, as you can see, total distance by the change in time. Now in this type of a pictorial representation, what I would like to show you is that this is the start of the interval. This is the ending of the interval. That means the interval ends over here, and we basically draw this kind of a straight line. Now let me show you this line, this purple one, which is connecting the both of the points. So from here, this is the end of the interval, and what I am trying to show you is that there is a straight line, and these are the two times, which is from 1 to 4. So these are basically the two lines, which are the 2 points, which is from 1 to 4. And I'm so sorry. So the vertical line actually shows how far it is moved from start to end, the vertical line, and the horizontal line actually shows where it is started and to end. Now as we are dealing with average velocity and average speed, etc., I mean to say we need to know what are the differences between the two. So I have shown the purple line, which is going up, and it is towards the end of the interval. This purple line is actually the vertical distance, how far it is moved, and the horizontal purple line is the distance, how long it took from start to end. So the starting to end is the how long it took, and the vertical is how far it is moved. Here is a quick, I would say, easy understanding of what are the relation between average speed and average velocity. So the definition, it tells the total distance traveled divided by total time, and this is displacement divided by total time taken. Quantity, this is scalar, this has got vector. Formula is delta x by delta t. In average velocity, it is basically total distance by total time. And for direction, this would be ignoring the direction, and it includes the direction of movement. For the feature, this is mode meters per second. An example, you can say this one, a car travel around 100 kilometers, so 2 meters per second. If the car end up, then it would be 0 meter per second. When it is used, it describes how fast an object move on a given path, and describes how fast an object move when it changes its position. Now I would like to show all these which I have shown you with a few more examples, so that the things become much clearer. Now say suppose you drive this truck along a straight road, and this is the straight road which is moving at 8.4 kilometers at 70 kilometers per hour, and suddenly at some point of time your fuel runs out. Right, your fuel runs out and the car stops. So what will you do? You get out of the car, and then you walk for 30 minutes. You walk to another 2 kilometer until you find another gasoline station. The question is that what is your overall displacement from the beginning of your drive to your arrival at the next gasoline station? Now, to solve this problem, we assume for convenience that you are moving in a positive direction. So first you start at x equals to 0 to a second, and then you move to x equals to 2, which is at the gas station. So the second position must be obviously this one. The path would be 8.4 plus 2, which is the total. It equals to 10.4 kilometer. Then your displacement delta x along the x-axis is the second position minus the first position, which becomes equals to 10.4 kilometer, which is basically the answer. So your overall displacement is 10.4 kilometer and it is in the positive direction of the x-axis. Now what is the time interval? Now I want to know what is the time interval delta t from the beginning of your drive to the end. Now, in order to know, we already know that the walking time interval, if I take it as delta t walk is equal to 0.50 h, then what we don't know is basically we lag the driving time, that is the delta t drive, for example. However, we also know that for the drive, the displacement of driving is 8.4 kilometer and the average velocity is 70 kilometer per hour. So this average velocity is the ratio of the displacement for the drive to the time interval that we drive. So in calculation, we write this one, delta x dr by delta t dr. We rearrange and then substitute the values and we get 0.12 hour. And then from delta t, we add those two things and we get the answer, which is 0.62 hours. Now there might be another question, that what is your average velocity from the beginning of your drive to your arrival at the station? I mean to say, you want to calculate what is the average velocity. Now, in order to do that, we just write the simple equation. Now, what is very much important to note is that this V average for the entire trip in the ratio is the ratio of the displacement of 10.4 kilometer for the entire trip to the time which we just calculated, if you can look over here, as 0.62 hour. So this is what is this part. So here we find V average equals to this by this, which gives an answer of 16.8, which can be roughly 17 kilometers per hour. And now in order to find things, if you want to do it graphically, you can see here, this is basically where the driving end and the walking starts. So this is where the driving end and the walking starts. This part is basically the slope of this line, which gives the average velocity. And this is again, as I was telling in the other part, which I have not shown, that how long does it take, that is the time, 0.62 hours. And this is basically the slope of this line, that is the average velocity, which is 6.8 kilometers. And this is actually calculated by V average, which is drives by land 10.4 by 0.62 kilometer, 62 hours, which gives around 17 kilometer per hour. So we got the how long, we got the slope of this line, and we got the driving, where the driving stops and how it starts, and we got the 16.8 kilometer per hour, which is the, and how do we calculate the V average, that is by rise by run, which we already got it to be so. So this actually brings us to another question, that suppose that to pump the gasoline and you have to go to the gasoline station. Here is the gasoline station, and you already have gone there. You have paid the money, and you are walking back to the truck. So you're from the gasoline station, you're going back to the truck, and for another 45 minutes. And the question is that what is your average speed from the beginning of your drive to the to your return back to the truck? So your average speed is what is the ratio of the total distance you move to the total time interval you have taken. So calculating, you can add the total distance 8.4 plus 2 equals to 12.4 kilometer, and the total time interval is as 1.37, which is adding 0.12, 0.5 and 0.7, and the equation finally gives result of this, and this is the answer, which is 9.1 kilometer per hour. So that completes our today's video on position, displacement, how do we calculate, and these are few of the easy calculations which will make you understand about how things happen. So that's all for today's video. I'm immensely thankful for those who have taken up time to watch. Please do watch and subscribe to my channel Physics for Students, and click on the bell icon to get all the notification from Physics for Students. You can also write to my email ID and subscribe to my other channel on General Theory of Relativity, and you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. Physics for Students will continue the classical physics, this entire course plus the other 4 courses which I have started. So see you soon, but till then, may the good Lord be with you.